Modern architecture relies on massive expanses of glass for natural light and aesthetic appeal, but this creates an immediate vulnerability in a building's thermal envelope. That vulnerability scales with the building. The thermodynamics of solar heat gain impact every structure utilizing flat glass, from homes to commercial high-rises. In residential architecture, extensive sunroom glazing creates intense localized heat pockets and heavy glare, rendering spaces uncomfortable during peak daylight hours. On a commercial scale, continuous structural glazing multiplies that effect, generating an exponential thermal load that forces mechanical cooling systems to run constantly. A common misconception in property management is that you can solve this heat gain by simply darkening the windows with cheap aesthetic dyes. But reducing visible light does not equal heat control. True thermal management requires modifying the physical properties of the glass barrier to reject heat before it enters. To do that, we have to defeat solar heat gain across three distinct physical mechanisms: radiation, conduction, and convection. Specifying a high-performance retrofit means moving past the concept of window tint and actively engineering this thermodynamic cascade. Let's strip away the building and look at the raw physics of a thermal envelope. This diagram isolates our starting point: incident radiation. This is the raw, unfiltered energy arriving directly from the sun, exactly as it exists before striking any atmospheric or architectural barrier. As shown in this image, radiation transfers heat through the vacuum of space, entirely due to extreme temperature differences. It requires no physical medium, no air, no water, to travel from a 10,000-degree sun to a 75-degree Earth. This incoming energy is not a single uniform wave. If we break this white beam down in the spectrum graphic, we see it is composed of distinctly behaving wavelengths: ultraviolet, visible, and infrared. The ultraviolet, or UV band, is the primary driver of material degradation. It breaks down chemical bonds, causing rapid fading in interior fabrics, flooring, and artwork. The visible light band is exactly what it sounds like, the portion our eyes process for illumination, which is also responsible for aesthetic glare. Finally, the infrared band. This is the primary carrier of raw thermal energy. It is the exact wavelength responsible for the intense heat gain inside a structure. Effective thermal control relies on spectrally engineering the glass to filter these specific wavelengths independently, rather than placing a dark dye over the glass to block them all equally. This simple jar test diagram acts as a proxy for a room. The glass creates a structural barrier, dividing the uncontrolled exterior climate from a contained interior volume. When incident radiation strikes flat glass, three things happen simultaneously. A portion is reflected away, a portion is transmitted completely through, and a portion is absorbed directly into the pane. Untreated architectural glass acts like a sponge for that absorbed thermal energy. As it soaks up infrared radiation, the exterior surface temperature spikes. This cross-section slice illustrates conduction. Conduction is the physical process where absorbed heat migrates through the solid mass of the glass itself, moving from the hot exterior face to the cooler interior face. Standard glass is a highly efficient thermal conductor. It offers almost zero physical resistance to this inward heat migration. This is exactly why cheap dyed window film fails. Dark dye increases the solar absorption rate of the glass, trapping more energy and turning the window into a hotter, conductive radiator. Blocking visible light accomplishes nothing if the glazing system continues to absorb infrared radiation and conduct it straight into the building. Once heat successfully breaches the interior surface of the glass, it interacts with the inside air. As conduction heats the interior glass, air molecules physically touching that hot surface immediately warm up. Notice the internal arrows in this jar model. They represent convection, the transfer of heat through gas movement caused by temperature differentials. This rapidly warmed air expands and rises, displacing cooler, denser air above it. That displaced cool air drops to the floor, rolls against the hot glass, and is heated in turn. This creates a perpetual thermal engine spinning inside the room. Look at the exterior arrows in this variation. If the surrounding environment is cooler, heat can convect outward and escape. But trapped inside a sealed room, the heat has nowhere to go. In commercial real estate, this continuous interior convective loop is the exact mechanism that triggers heavy, sustained mechanical loads on the HVAC system. Once solar radiation converts into interior convection, the building's thermal envelope has failed. At that exact point, you have to spend mechanical energy and money to pump the heat back out. To prevent that failure, the industry relies on advanced ceramic and IR rejecting films. This side-by-side comparison reveals the core mechanism. These films operate exclusively at the initial radiation stage. Instead of absorbing energy, they selectively reflect specific infrared wavelengths away before they can penetrate the surface. By reflecting radiation immediately, you completely short-circuit the conductive and convective phases. The heat cascade never even starts. Understanding these physics dictates exactly what kind of product a contractor specifies for a given project. In a residential setting like this, homeowners prioritize high visible light transmission to preserve views, paired with aggressive UV rejection to stop fading. Spectrally selective films meet these demands, providing extreme thermal comfort without making the interior feel dark. But on a commercial scale, priorities shift. Massive glazed facades require maximum total solar energy rejection for a measurable return on investment against HVAC costs. Large-scale deployments utilize advanced films to aggressively slash cumulative convective loads across thousands of square feet. Professional window film application is active, precise thermodynamic management, applied directly to the building's most vulnerable thermal barrier.